I'm going to start this introduction to vision, or really the introduction to the eye, by talking about the properties of light, and then actually introducing the eye and the optics of the eye, or the mechanics of the eye. And then on Monday, we'll finish up with the eye by talking about the photoreceptors and what's happening at the retina. As I've tried to say, but now I'm going to say with a slide so that you see the words together, the visual stimulus, or what is out in the world, so the environmental stimulus, is electromagnetic energy or electromagnetic radiation, which is light. And there are two ways to conceptualize light. I think most people, this is kind of more in mainstream knowledge now, but I remember, I think I learned this in sensation and perception class, where it can be a wave and it's moving around in the world. We talk about it as moving as a wave, but it's also light is made up of a stream of photons, and so we're going to talk about it in this way too. When it's absorbed by the photoreceptors, when it's absorbed for us to understand it, we're absorbing photons of light, the actual particles of light. So this electromagnetic energy that we get to see, we are able to perceive a very small sliver of the electromagnetic spectrum. What we get is about, depending on the estimate, which it sometimes changes, between 360 to 700 nanometers, where a nanometer is a billionth of a meter. This is unfathomably small, these little waves that are moving through the world. As we get into shorter and shorter wavelengths, if you look up at the figure that's kind of in the top right of the picture there, from peak to peak is our measure of wavelength. And as this gets shorter and shorter than 360 nanometers, which again, we can't even really comprehend, we get into ultraviolet rays, X-rays, and gamma rays. And there are animals that perceive this ultraviolet part of the spectrum. So if I remember correctly, there are some birds, I think butterflies, and there are some fish that are down in that ultraviolet part of the spectrum of what they see. As we get above 700 nanometers, so longer and longer wavelengths, we get into infrared rays, radar, FM, TV, AM, and AC circuits. There are animals that perceive that infrared part of the spectrum. If I remember correctly, there are some fish and also snakes. So when snakes are sticking out their tongue, they are using their tongue really to perceive heat sources, which is telling them about the infrared information. So they're kind of, you can kind of put seeing in quotes, they're kind of seeing the world with those infrared rays. So we get our little tiny sliver. I often say I think we're lucky to get that little tiny sliver, as if we saw everything from AM information to X-rays and gamma rays. I think it would be very overwhelming. That again is just talking about the wavelength information. If you go back up to that top right part of the figure, there's also amplitude. So from trough to peak, how high does the waveform go? And that's giving us information about brightness. So are we out, or am I something red that's out in the sunlight and reflecting that sunlight, and I'm actually very bright myself, so I'm reflecting that sunlight? Or am I that same red shirt and I'm under a dim light? I'm going to have a lower amplitude because I'm not quite as bright. There's also a kind of purity to the waveform or mix. So what is being shown in the figure is a perfect sine wave, or what's called a sinusoidal waveform. And what's being shown with the white light going through the prism. So if you have prisms in your windows or on your car, whatever, what's happening when the sunlight is going through that prism, or when we are creating rainbows with water, and water is refracting sunlight, what we are seeing are those perfect waveforms. Okay, so pure Roy G. Biv, red, orange, yellow, green, blue, indigo, violet, as we're getting into shorter and shorter waveforms, and they are these pure sine waves, or these perfect sine waves. But usually, actually, what we see. So I'm wearing right now a red shirt with a yellow emblem, and my red shirt is not rainbow red. There's some mix in there that gives a different kind of experience of saturation. And the dominant waveform is going to be that kind of longer wavelength, but there's going to be some wrinkles in it. It's not going to be that nice, perfect sine wave. And the little yellow emblem, the dominant waveform, is going to be this more closer to a medium wavelength. But again, it's not going to be perfect like what we're seeing in the top in A. It's going to have some wrinkles in it, depending on exactly what kind of yellow and how saturated that yellow is. We'll talk more about the aspects of the waveform when we get to color vision towards the end of the semester, but just so you see, these are the properties of light and how that's translated into perception. I'm going to start with the optics of the eye now, so how we are going to take that light so that we can understand it, something the brain can understand. It actually starts with the optics of the eye, which are really quite incredible. So we're going to start out there with the cornea, that kind of clear outside part of the eye. It is refracting or bending the light, and actually that cornea has about 65 to 80% of the focusing power, and that 65 to 75 or 80%, it depends on what you're reading, that estimate. So I'm not exactly sure where it is, but it's somewhere in there, but it's doing most of the focusing. The pupil, what we see is that like black part of the eye, that's actually a hole in the iris where we're letting the light through so that it can. So if you're looking at the picture at the bottom, this is an eyeball looking at a tree, that light information is being reflected from the tree. It's going through the pupil, and it's being refracted and bent in such a way so that it turns into this upside down inverted kind of image on the back of the eye. So we want to let that light into the back of the eye, to the retina, so that we can use that information. The pupil is a hole in the iris, and the iris really refers to the muscles that are constricting and dilating the pupil, and that constriction and dilation depends a great deal on light level. So if I'm in the dark, my pupil is going to get larger and larger to let in more light, and then I walk out into where it's sunlight, and my pupil is going to get smaller and smaller so that I let in less and less light. The iris is the colored part of the eye. This is really depending on the person's pigments as what color their irises are. The lens helps to focus the image on the retina. So it's doing the rest of the focusing power that the cornea is not doing. It's really, as we're going to talk about, it's what really lets us change our focus so that we can look at something close and it's in focus, or look at something far away and that's in focus. So the cornea, it's not changing in any of that. It's just doing the bending that it's doing, and it's the lens that's helping us to focus depending on where, or depending on what we want to see and where it is in space. And we have some more muscles here, the ciliary muscles, that are going to control the shape of the lens. So either allowing it to become more kind of flattened so that we can see something far away, or letting it become fatter and fatter so that we can focus on something that's up close. And what the picture is showing is not just the kind of optics of the eye and the reflection of the tree being refracted and bent in such a way that it's upside down and backwards back on the retina, but it has this magnification back there of the retina, which we will talk about again as we move forward, because we're going to talk about the rods and the cones, which are actually our photoreceptors. They're going to be changing that electromagnetic energy into electrochemical energy. And then in front of that, right, so the light's coming from the front of the eye, going through all of the parts of the eye, and then those neurons. There are neurons that are then going to communicate out to the brain. And behind the rods and cones, that kind of just really dark gray band back there, that is the pigment epithelium. I'm going to talk about that a little bit today, and I think I probably don't talk about it much more, a little tiny bit with dark adaptation and so forth, but that's really what's nourishing the rods and the cones. And if you want to keep that pigment epithelium healthy for as long as possible, you are going to want to take your omega-3s and your zeaxanthin and your lutein. So those are your carotenoids. Those are vitamins you can take, but also you can just eat a lot of fish, especially those smaller fish like mackerel and sardines and things. I think salmon has a lot of fat, so that's a good one. And avocado actually has those omega-3s. And for the zeaxanthin and lutein, you can eat your green leafy vegetables, and those will give that to you naturally. Additional parts of the eye include the aqueous humor. So between the cornea and the lens, there is this fluid that is supplying oxygen and nutrients and also removing waste. We can also keep that healthy. My understanding or memory is omega-3s and vitamin C, as that again is really providing nutrients to the cornea and lens, which we want to do. The vitreous humor, which is that gel-like substance behind the lens, and really, so I usually do this in class where I say kind of just underneath where you're still under your eyelid, but you're not touching your eye. But kind of poke your eye real lightly. Don't poke your eye, but poke your eye real lightly, and you can feel it's kind of gushy. It's kind of gel-like. That's because of the vitreous humor. This is actually also where we're seeing floaters, as they are called. So I get them. I've always gotten them quite a bit. I don't know if everybody gets them as much as me, or if I just notice them more. But if you're kind of looking out at the world and you see this little tiny gray dot that moves around, and if you try to look at it, it moves out of kind of your field of vision. I feel like I get them more and more since I've gotten older. But those floaters are pieces of vitreous humor, and they are absolutely normal for all of us. If we continue to move to the back of the eye, so what's actually being shown in that magnification is the retina. This is where vision actually occurs, so where the action takes place. Really only half of the light that enters the eye makes it here, because it's going through all of that, but both of those humors, and then if you look at the very back magnification, it's going through those neurons before it can hit the rods and the cones, which are the photoreceptors. That's where we are doing the transduction, so where vision is occurring. And we have the fovea, which is tightly packed with cones, and so this eye looks like it's looking right towards kind of the middle of the tree, and we are trying to get the best kind of detailed, most acute kind of color information from where we are looking at the center of that tree. And then we also have a blind spot. So if you see at the back of the eye at the picture, there's this optic nerve leaving the eye, where we're going to take that information to the brain. And along the same kind of area, we have blood vessels coming into the eye to also nourish the eye. Again, the goal of all of these optics of the eye is to focus light on the foveal retina. So as we're moving our eyes around the world, we are trying to get this more acute version of the world. So as you know, when you try to read, you can pick up your textbook or any kind of book and look at it. You can only see the letters that you are looking directly at, and those are the letters that are landing on the foveal retina. So we move our eyes to get that really detailed information. Some of this has a lot to do with accommodation. So we're going to change the shape of that lens to change and adjust the focus. And I usually do this demo in class, but please think about doing this. I'm gonna do this as I'm talking because I think it's important. So go ahead and pick up a pen or a pencil or something and put it in front of your face. And so I'm looking off at the wall of my house. And as I'm looking off at the wall of my house, what's happening to my lens is it's getting kind of flattened out. And as if you notice the kind of the pen or the pencil that you're holding up right in front of your face, that is getting kind of blurry. You might even have a kind of double vision of it. Okay, and as you look then and change your focus to look at the pen or pencil, which is right in front of your eyes, but then you're kind of noticing the wall of your house or whatever's off in the distance, what you'll notice is the pen or pencil is in focus, and the wall of the house, there's kind of this double vision and really kind of blurry vision. So we're changing the shape of that lens depending on what we want to focus on, and what we want to focus onto the foveal retina. Again, the goal of all of these optics of the eye is to focus light on the foveal retina. So as we're moving our eyes around the world, we are trying to get this more acute version of the world. So as you know, when you try to read, you can pick up your textbook or any kind of book and look at it. You can only see the letters that you are looking directly at, and those are the letters that are landing on the foveal retina. So we move our eyes to get that really detailed information. Some of this has a lot to do with accommodation. So we're going to change the shape of that lens to change and adjust the focus. And I usually do this demo in class, but please think about doing this. I'm gonna do this as I'm talking because I think it's important. So go ahead and pick up a pen or a pencil or something and put it in front of your face. And so I'm looking off at the wall of my house. And as I'm looking off at the wall of my house, what's happening to my lens is it's getting kind of flattened out. And if you notice the kind of the pen or the pencil that you're holding up right in front of your face, that is getting kind of blurry. You might even have a kind of double vision of it. Okay, and as you look then and change your focus to look at the pen or pencil, which is right in front of your eyes, but then you're kind of noticing the wall of your house or whatever's off in the distance, what you'll notice is the pen or pencil is in focus, and the wall of the house, there's kind of this double vision and really kind of blurry vision. So we're changing the shape of that lens depending on what we want to focus on, and what we want to focus onto the foveal retina. So I usually stop here with a picture that is again showing the whole, this is what's out in the environment. It's being really bent by the lens and the cornea, and they're acting much like a camera lens, but it is, they are refracting that light so that the cup is now an image on the back of the eye, on the retina. It's an upside down inverted image. And if you notice, it's going through all those, it's going through the aqueous humor and the vitreous humor, and in the back there, this kind of magnified area, it's going through all these neurons before hitting the rods and the cones. And the rods and the cones are what we're going to talk about for a little while as doing the transduction and how they do this transduction. They are the ones that are absorbing those photons of light so that we can see our visual world. And again, back there in this kind of gray, dark, kind of almost black line is the pigment epithelium, which we want to keep as being as healthy as possible because it is nourishing the rods and the cones. I'm going to talk about some of the clinical issues of what can happen with the optics of the eye. So what I think is most common in most of us, if we don't actually have it, we at least know somebody who has it, right? You guys know me. So Myopia is a word for nearsightedness, which means we can see things that are close, but things that are far away are difficult to see. And more than 70 million Americans have some form of myopia. There's more myopia in developed nations where we are spending a lot of time looking at screens, being close to TVs, looking at reading up close and all of that. So some of this is environmental. It's also somewhat genetic. And some people have this more refractive myopia where what's happening, this is kind of shown, well, however you interpret A there. So the cornea and or the lens are refracting the light or bending the light too much, and so it's being focused somewhere in the middle of the eye, so somewhere in front of the retina. And what we can do is we have some kind of far point. Mine is actually very close. If I hold up my sensation and perception textbook at arm's length, I can kind of tell that it says sensation and perception, but that's only because I've seen it for a long time. It's just a blurry bunch of stuff that I can kind of make out, but even at arm's length, that's not, my far point is closer than that. So we have this far point, and the way we correct for myopia is to give us a kind of concave lens that makes those, so when we're looking far away, when the light is reflected, it's coming in more of a parallel fashion. And what B is kind of showing there is when something's closer up, the light is, when it's reflected into our eyes, it's coming in at this kind of wider angle. And so we have a corrective lens that takes that more parallel light being reflected and gives it to us at this angle so that it gets refracted in such a way that it's being focused on the retina. So sometimes that is refractive myopia, where the lens and or cornea is bending the light too much. Sometimes that's an axial myopia, where the eyeball itself is too long. My recent experience at the eye doctor suggests that I have an axial myopia, because he said your eyes are bad enough that given the shape of your eye, it's more likely that you're going to have this kind of retinal detachment, and as you get older, you probably want to come in more often. So that was an unpleasant experience from my perception. But but we can wear these glasses that correct for that, and we can see just fine. There's also hyperopia, or farsightedness, where the lens and or cornea is not bending light quite enough. So when it is getting bent, it's being focused behind the foveal retina. And here we just have a different shaped lens, right? So these people instead have a near point where it gets more and more difficult to see. And we want to make that light a little bit more parallel in order for them to see. And I think your book talks about how not many people who are young have this, I'm going to talk in a second about presbyopia, this kind of old-sightedness, that we're going to become more and more farsighted as we age. But there are young people who have hyperopia. It's just not very common like myopia is. There's also presbyopia, or old sight, as it is called, which I resent or resemble. I resent. So I am 50 years old, and I can tell that this is happening to my eyes. What happens is that lens needs to get really fat in order to bend the light enough when it's coming in at that angle, when it's close to us. And the ciliary muscles get weaker, that lens gets kind of harder or more crystallized, and that gets more difficult as we get older. So I watched my sister, who's a few years older than me, as she moved the menu farther and farther from her face, as her near point, what she could see that was close to her, got farther and farther away. For me, they've done something really different in giving me these kind of transition lenses, and really for me to see something up close, I just take my glasses off because my eyes, because I'm so myopic, that works for me. But everybody, sometimes starting around the age of 40, sometimes a little earlier, sometimes a little later, we start to get this presbyopia, where we need those readers or those just a little bit of magnification. I think I'm going to run just about a minute or so over here, but for my summary slide, I'm actually doing a let's look forward slide. So the next class, we're going to finish up by talking about the retina, specifically the rods and the cones, those photoreceptors that are doing the transduction. And we'll talk about transduction itself. But also before that, we'll go through the differences between those photoreceptors. So they differ, the rods and the cones differ in their physical appearance, in their distribution along the retina, or where they are, the wiring to the brain, which influences both our acuity of what we see from the cones and the sensitivity to dim light, what we see in the rods, the clinical issues of what can happen and what we see if either one is damaged, which between that and the wiring, it really gets us to our functional significance. For the most part, that'll make the functional significance really clear, but then we'll talk also a little bit more about color vision and what the cones give us and how they give us that color vision. So this is it for Friday's class. I hope everybody has a wonderful weekend and everybody feels comfortable coming back to classes. I don't know if people are actually watching this. I haven't gotten a lot of questions, and I'm just hoping that everyone feels like they know what's going on at this point, but do let me know, and I'll talk to you all on Monday. Have a good weekend.